Hello, welcome everybody to another tutorial discussion on the IQ3 for MATH155 Summer Session 2020. This IQ is based upon, one of the most beautiful theorems, as I mentioned before in our chats and stuff, where this is the fundamental theorem of calculus. What it does is it'll give you a new perspective towards, looking at things that you've been solving like pointlessly all the time. Okay, so I want to try to take a second before we start to begin this assignment to kind of give you a motivation behind what fundamental theorem of calculus is and how do you, effectively use its expressions and the powerful tool to help you answer all the questions that you've been seeing on your OQs and IQs. Okay, so let's jump back to the motivation for that part first, and then we'll come back to the questions. Okay, so what we're trying to do here, I'm trying to use these notes that I produced before to kind of walk you quickly through the concepts of what we're trying to talk about here. Okay, so far what you've done is, if you were given a definite integral from a to b of a function, okay, the only way to calculate that is using Riemann sums. Okay, that's all what you learned. To find an integral, you have to do a Riemann sum, and then you gotta accumulate all those little rectangles to kind of give a reasonable approximation to the area. That's exactly what we did in the IQ2. So I'm gonna recap here a bit. We have, a function x cubed. You want to find the area under the function on the interval 0 to b. So basically what you're looking for is the integral from 0 to b of x cubed dx. Okay, and to do that, all we had to do is we have to construct, the Riemann sum approximation, and then to finally notice that the Riemann sum limit as n goes to infinity is pretty much the area under the curve, and do that all of this looks very hideous in computational calculations, something that you don't want to do every single time when you try to solve an integral. So this is where we're going to start to see the motivation towards introduction of fundamental theorem of calculus. So we saw that computing areas as Riemann sums can be very tedious and long. Okay, so what we do, we try to bypass this and we try to find a function. Okay, so now we're going to try to find a function, so literally an expression that you can use, which will take an input x. Okay, so you give it an input x, and it gives you the area from any starting point till that point. Okay, so now it's a little bit wordy, but let's try to put this into the vision of it. So we can say the function a is the area function, and this will depend upon the x that you choose, because you have to specify the end point of an integral. Okay, so that's what we're going to do. We're going to call the function area function the a of x. That gives you the area up to some x point. So to write it in terms of the integral of f of t, the area function x is going to be the integral from some starting point a, which is going to be a constant, to some x that you choose, which is pretty much the variable of this function, of f of t dt. Okay, this is what I will start by basing off that argument. Okay, I'm trying to find this magical function. I'm trying to find what this a of x is that does this property and obeys this relationship. Okay, so let's try to look at the graph for a second to kind of visualize better. Here in this case, this is some random function f of t, where this axis is denoting t, and this is the function's f of t values here. And we're starting at some point a, and we're going up to some x point that has this arrow. The reason why I have an arrow, because this could be movable. You can move the x to any number you want, okay, and the function will take that as your x input and will spit out the area. Of course, if you move this x to this point, right, let's say at this point, then you're going to accumulate this extra area as well, so that the function will spit out this total area that you accumulate here. Okay, if you want to move this x here to this point, then you will have to spit out this integral area. Okay, so you can move that x. Of course, it makes sense if x is equals to a, so you move the slider all the way back to a, then you're not going to enclose any areas, because both the things will line up on each other, right? So you won't be able to have any area coming up there. So let's say this is my function, okay, and what we're trying to do is we're trying to observe what happens to this function if I change my input by a slight number. Okay, so what I did here in this portion is I bumped it up by a little amount of what we call h. In this case, h is just some small extra x distance that you move this. Okay, so what you see here is that this area is a of x, So because now you're at x plus h now, all of this portion here is going to be the area of x plus h, because that's the function, right? We should just specify it the initial point, the part, and then it'll just split out what the area is up to that point. So if you put a of x plus h into there, a of x plus h will give you the whole area. So now remember, because up to this point, this area, this portion here, is nothing but a of x. And then this whole thing, including a of x, is the area a of x plus h, because it accumulates all the area up to that point, right? So that's what you're getting here. Now, the thing that I want you guys to see, very importantly, is that when you bump it up by a little amount of h here, what happens is you're going to have this extra area here, which I have approximated using this rectangular portion here, which we call extra. Okay, so basically the difference between those two areas, the difference between the area up to x plus h and the area up to x, should be equals to the area of this little rectangle that you have called as extra. Okay, so we're going to see that here. When you move added h to the x, what you're going to get is the area went from a of x to a of x plus h. And the extra area, which could be figured out as the new minus the old. The new is x of a of x plus h, minus the old one is a of x, which can be approximated by the new rectangle we call extra. Okay, that's what the idea is. So we know the difference between these two, okay, will approximately be equal to the area of extra. And how do you find the area of rectangle is probably a very old school question for you guys. The area of rectangle is the height times the base. Okay, the height here, I'm using the left point notation for that. The height is just going to be the value of the function at that x. Okay, remember that. So at this x value is what the height is going to be here. So that's f of x for the height, and the base is h. Okay, so what you see here is that this area of extra is just going to be the height times the base, like this, right? And then if you do a little bit of rearrangement, what you can do is you can figure out that f of x, okay, from that isolation, is roughly equals to the difference of area with the x plus h minus the area of x divided by h. Okay, and this computation, okay, this argument becomes way more accurate if you make a very tiny adjustment. Okay, if the h that you added is very small. Okay, so that is more accurate at that point. Right now you see this extra approximation here, but if you move that h to be very small, or in other words take the limit of h going to 0, you're gonna get virtually exactly the same extra approximation here. So this expression will make more sense. It will be more accurate if you choose h to be a very small number. Okay, now this is where it's kind of like the giveaway here. We know that the result gets more accurate if that h was super tiny. So we take the limit of h equals to 0, and this expression is something that you should get a flashback from the previous math calculus 1 course that you guys did. Okay, this here is the fundamental definition of a derivative. So what we've done here, just to recap quickly, is we started off looking at a function area, the area function a of x, and we try to see what kind of relationship do you think it observes with the function that you're trying to integrate. And we figured out that the relationship that it obeys is the function that you're integrating, which we usually call as the integrand. Okay, this is the function that you're integrating. The integrand function is nothing but the derivative of the main function. Okay, this is the very crucial part. So this is what the conclusion is. After analyzing all of that work, we know the function that's actually inside the integral is nothing but the derivative of that area function of the magical function that we want to look for. Okay, so this is very important. This is the concluding statement. The area function is the antiderivative of the function that we're integrating. Okay, and this right here is the fundamental theorem of calculus part 1. What you can do here is use this to kind of simplify your answer very easily. So you say we can find an area function simply by taking an antiderivative of the function that we're integrating. So just to like kind of come back here, if you were trying to integrate, this function of x cubed from 0 to b, what you want to find is you want to find a function, first of all, a function whose derivative is x cubed. That's how you take an antiderivative. To find an area function, okay, you have to ask yourself a question: what function do I derive in order to get x cubed? Okay, and that's the process of taking the antiderivative. This is what helps you figure out this idea. And you can find an antiderivative of a function, and you can use the integral to compute that number very easily. This is where everything changes. The area under the curve now can be found by taking antiderivatives. Before, you have to do that by doing rectangles and adding them up using Riemann sum, but no longer anymore. Okay, you can use this thing. So that's where the fundamental theorem part 1 comes in handy. I'm gonna write it down here so you guys can see for like the portion of it. So if we have an area function that we're going to call a of x, which takes the integral from some starting constant a to some x that we choose as the input of a function f of t dt. Remember, f of t dt or f of t is basically the integrand function, the function that we're trying to integrate. If we have this, then the derivative of the area function with respect to x is nothing but the function that you have plugged in x. This is the fundamental theorem of calculus part 1. Okay, very important. So if I would want to like iterate a second for like this, what you have to see is the very shorthand notation is that the derivative of the integral, because area function is just this integral. So derivative of the integral is the function itself. This is what concludes the whole story for the fundamental theorem part 1. Okay, so now if you are looking for an area function, you should be, in other words, looking for the antiderivative of this function, the function that you're integrating. Okay, that's fundamental theorem calculus part 1. That's it. So now part 2 kind of builds on the given information. So part 2 will have a situation here. A part 2 tells you that what you're looking at, I'm going to try to put this on top of it so we can easily write it here. Part 2 tells you if, let's say you have a function, if a function capital F of x is the antiderivative of a function small f of x. So this is given. You're given this. If you can find a function, which we call it as capital F, which happens to be the antiderivative of small f, then the integral from a to b of f of x dx is simply capital F of b minus capital F of a. And this right here is the fundamental theorem part 2. Okay, first of all, the first part tells you that the relationship an area function must obey with the small f of x function is that the derivative of the area function is the function that you're integrating itself, hence telling you that integrals and derivatives are inverse processes. Okay, it's inverse operations on each other. So if you're taking a derivative and then you're integrating the thing, you're gonna get the same thing. Okay, that's pretty much it for the part 1. And then part 2 uses that information to kind of give you a qualitative way to find numbers and numerical answers. Okay, if you know a function's antiderivative, then its integral from a to b is nothing but its antiderivative's value at b minus the antiderivative's value at a. Okay, that's pretty much it. That's what like the smallest summary I can provide. Okay, this will not show you the whole picture. Of course, if you have any questions, you can definitely come back and talk to me. I'll be more than happy to help you out. But now, without further ado, let's start off with the assignment. Okay, what we're doing here in the first part is we have area of a leaf, okay, which they have kind of like cleverly made in this case like this. So I'm going to try to give a picture here. What it said is this edge of the leaf could be approximated by a function which they call f of x here, and the function is given like this. Okay, so this edge here is the edge f of x. Okay, and then they have another edge of this leaf, which is we call g of x. This is given like this here, and they want you to figure out this area. Okay, I'm trying to use which color. I would use this yellow. So they want you to figure out this area. Okay, so just like to visually draw what we're looking at, if you would only do the area of, you know, just f of x, right, which is the top function, then you're going to get all of this area. So if you were to integrate from 0 up to this number 5 here of f of x dx, then you're going to get this area. Okay, but this edge of the leaf is something that you want to get rid of. So you want only this area. You want to get rid of this portion down there. Okay, so how you do that in terms of integrals is if you see the area under this curve is this red shaded portion. Okay, this red shaded portion is pretty much the integral from 0, because this point is 1. Okay, so from 0 to 1 of this function of g of x function. So the red portion that you see here in the shaded part is the integral 0 to 1 of gx dx, and this whole integral will give you the total area. So what you want to do is you want to take the total area from 0 to 5. Let me just try to erase this. It's turning out ugly. So you want to take the total area from 0 to 5 of f of x dx and take away the portion that you don't need. So that portion is this red portion that you don't need. That's 0 to 1 of g of x dx. Okay. The simpler way to break down this problem is also another way if you're not trying to look at this in this way. You can break these up into different portions. Okay, where you can kind of assume this. Let me try to redraw this a bit so you can figure it out that way. So now, if you have it in this format like this, I'm going to draw this line up here, okay, where this is 1, and now you have a 0 and you have a 5. So you can visualize this as two different portions. But I'm going to call this portion as the A portion, and this other portion I'm going to call as the B portion, right? So if you think about the portion B is nothing but the integral from 1 up to 5 of f of x dx, because it just covers up the area under the function f of x, right? From 1 to 5. So that's this. So B portion is like this. But for the area of A, what you want to do is, if you will kind of like think about it, the area under this function, the f of x, is the whole thing. Okay, but you want just this green portion that I shaded over there. So you want to get rid of this extra area from the bottom. So what you can do is you can find the total area, take away the red portion to get the green one. So basically the portion A is nothing but the integral from 0, because it starts at 0 to 1 of the top function, which is the f of x function, and then minus the portion that's in the red shaded portion here in this case, okay, which will be the area under the curve g of x from 0 to 1. So this is how you're going to do that, how I actually did it in my solution. So there's multiple ways. As long as you get the same answer, there shouldn't be a big trouble there. So let's look at the workings now. So what you want to do here is to see the upper half will be calculated over two intervals. I made it from 0 to 1 and then 1 to 5. Okay, so in the 0 to 1 region, the area that you're interested in is the area under the f of x function. Take away the shaded red portion, that's the area under g, right? So we did that portion here, 0 to 1 f of x minus 0 to 1 g of x. And now what you can do is you can combine them here under the same bounds here, from 0 to 1 of f of x minus g of x. Because you have the same bounds here, you're just taking the subtraction of a different function. You can take them under the same integral sign, subtract first and then do the integral. Okay, so now I'm going to try to plug in the functions that were given to us. So f of x comes in right here, g of x comes in right here. Okay, I'm going to solve that bit in a second. Now for the other portion, 1 to 5, the area that we're looking for is just the area under the f of x function. So from 1 to 5, area under the f of x function could be given by integral 1 to 5 of f of x. So you just plug them in there, and I haven't solved it yet, but I'll simplify that in a second. So the total upper area is this integral that you found out here plus that integral that you have there. Okay, so I rewrote that thing here with this integral in mind, and then plus the other portion. So this pretty much kind of gives you the portion A that we have in the previous picture, and then this is the portion B. Okay, so we got that. How do we solve these integrals? We'll talk about that in a second. Okay, so we got this expression here. Once you simplify this, if you expand the x minus 1 whole squared, you're gonna get x squared minus 2x plus 1, and then you do the algebra. When you combine all of these things, you're gonna end up with this expression simplified in the formal way. So that's out of the picture. This one was already simplified, so there's nothing much to do here. We'll keep them in this form. So now here they want you to use FTC2. When they say use FTC2, you got to use fundamental theorem of calculus part 2. So let's recap. Given that you know some capital F, that is the antiderivative of the small f which you're trying to integrate. If you know this, then the integral from a to b of that f of x is just the antiderivative plugged in the top bound minus the antiderivative plugged in the bottom bound. Okay, so now how do you find the antiderivatives? To find the antiderivatives of any function, you have to ask yourself a question. You're looking for a function that you will derive to get this guy. Okay, so to find the antiderivative of negative 1.12 x squared plus 2.4x, the question I have to ask myself is, what function should I take the derivative of to get this thing? Okay, and that is the formal way of taking an antiderivative, which we already know as the power rule, which some of you might already know how to apply. So I'm keeping that in mind here. So you do that, the antiderivative of this function is going to be negative 1.12 divided by 3 times x cubed plus 1.2 x squared plus some arbitrary constant c. Okay, because if you want to check yourself, you can take the derivative of this function and you're going to get this guy. Okay, so if you take the derivative of this function, you're going to get this guy. So that's a good way to cross-check your answers. Where the c, when you take the derivative, will go away because it's a constant, right? So the derivative of a constant is 0. So never mind about that. So that's one portion solved. We know the antiderivative of this guy. Now we need to find the antiderivative of that function. Okay, similarly, we do the same approach. The antiderivative of the other function that we have is just going to be this guy here. The reason why I want to leave this up to you to decide is because this skill is something that I want you guys to develop yourself. Okay, these are the power rules, the very basic rule of taking an integral. If you want to cross-check your answer, what you can do is you can take the derivative of this guy and see if you get this or not. Okay, this is where the condition is. So the answer to the question of what function should I derive to get this is this guy, where c is again an arbitrary constant. So now that we have antiderivatives, we know capital F's for both of the functions. So now we can evaluate the integrals. So evaluating this integral would mean plugging 1 into the antiderivative minus plugging 0 into the antiderivative. So we know the antiderivative is right here. All we got to do is plug in 1 first in all of these places, and then take away, plug in 0 in all these places. When you do the math and you work out the numbers, the c's will cancel out. you're going to get left with just this number there. Okay, be sure to try it out yourself. Okay, make sure you kind of figure this out yourself. So that's this. And then for the other portion, when we're trying to do the integral of this guy, when you have it, you know the antiderivative here is just the function that you solved here. And all you got to do is plug in 5 in that function minus plug in 1 to the function because of this guy. Okay, so the integral of this function is pretty much plugging in 5 in the antiderivative minus plugging in 1 in the antiderivative. And when you do the math, by expanding all these numbers and working in nice fractional numbers, you get 96 by 25. Okay, feel free to check your answers again. If you want to do that, I double check them. Okay, so because we got the total area as the sum of these integrals, what we do is we add up these numbers. So when you add up 62 over 75 plus 96 over 25, your final answer is going to be 14 over 3. Okay, so the area, the surface, the area of, you know, the leaf's upper portion is just 14 over 3. And now what they want you to do is use symmetry to find the total area of the leaf. Okay, so the total area of the leaf is the, you know, the top portion and the bottom portion combined. Since the top portion and the bottom portion are symmetrical, and the top portion has an area of 14 over 3, the total area is nothing but twice of that if you only consider the top face, which is the usual case. Okay, there is an ambiguity, of course, and I'm pretty sure you guys can clarify that for yourself as well. If they want you to find the area of the leaf on both the sides, then you gotta do 4 times the front area. Okay, but in my perspective, there's only one face of the leaf that's, you know, responsible for chlorophyll and all that food production that you have over there. The back portion of the leaf usually doesn't have any chlorophyll happening, so we usually tend to ignore that. But if you guys still have any questions, like you should 4 times the area or double the area, please definitely ask your prof, or, like, you know, clarify with your classmates and whatnot. But I think this should be it. Twicing it, the area should get you the right answer. And that's pretty much it. This is how you do the first problem here. This is based upon FTC Part 2. So now we're going to go with the more interesting one, which is based upon FTC Part 1 here, where the graph sketching is coming in. So you gotta come back and brush up a little bit of your skills from the previous calc course that you did, because we're going to talk about graphs here a bit. So now what they've given you is, they've considering this function, they've defined an area function, which is the capital G of x, that spits out the area under the graph GT from -2 to some x that you choose. Okay, where x could take any value between -2 to 5. So that's pretty much it. So that is the definition of the area function that we have here. So now, because we got to pay attention to the starting point, the attention to the starting point is if it starts at -2, okay, and then you're going to start to sweep the area. Usually what happens is, if the top bound of the area function is bigger than the bottom bound, okay, you're going to get a regular convention. The regular convention is that you're going to get positive areas if you have a positive graph, and you're going to get negative areas if you have a negative graph. Okay, we'll talk more about that in a second once we see the graph down there. What we have to realize is, from FTC Part 1, is that this function, aka the area function, and the integrand function, aka, you know, the function that you're trying to integrate, obey this very specific relationship. Okay, so the derivative of the area function is nothing but the function itself that you're trying to integrate. Okay, keeping that in mind. So that the given graph that you have down there, this graph here, is a graph of small g of x, small g of t in this case. Small g of t is nothing but the graph of the derivative of g of x, because they obey this relationship. So keep that in mind. Okay, very important to keep that in mind. Now, the first part of the problem is asking you for the intervals where capital G is increasing. So how do you answer when a function increases or not? You got to go back to your Calc 1 course, and you know, you'll probably realize that the function is increasing when its derivative is positive. Very straightforward answer, right? So we're looking for the interval where the derivative of capital G is positive. Now, because of fundamental theorem of calculus, we know the derivative of capital G is nothing but the small g function. So all we gotta do is look at the graph and see where the function is positive. Because if you see this graph here, this function is negative in this portion, then becomes positive in this zone here, okay? Then becomes negative again, and then becomes positive here in this portion, okay? So this graph is nothing but the graph of the derivative of the capital G function, okay? So this has every information that you need. So if you want to answer where the function is increasing, all you got to do is see where this function is positive. And those points are this point all the way up to that point, and this point all the way up to 5. So to approximate, this point is probably going to be negative 1/2, and up to, this point, which is 3, and then 4 to 5. So the interval where this increases is from negative 1/2 up to 3, union 4 to 5, because that's the zone where this graph is positive. Having this graph positive means the derivative of capital G is positive, and having a positive derivative means the function is increasing. You can apply the same thing on the other portion where they're asking you the decrease. The reason why I included that here is just give you better practice, okay? We're just looking for the increasing interval, but just for the sake of it, for the decreasing part, you can also answer that. If you see, for the decreasing, all you have to specify is the interval where the derivative is negative. And to find where the derivative is negative, all you're looking at this graph is the points where it's below the axis, right? So this function is negative from -2 to -1/2, and it's also negative between 3 to 4, okay? So the function is decreasing from -2 to -1/2, union 3 to 4. These are the points where you're going to have that thing, okay? And now this information will become in handy when you try to do the B part, where they're asking you estimate the values of x, so there could be multiple, that there are local minimums of G. Okay, you want to find where you have a local minimum for G. So remember, capital G is a function whose graph is not given to us yet. We should be able to pull out this information from its derivatives graph, because that's what we have on hand right now. So to find a minimum of capital G, I want to ask you to kind of think and, kind of just like revise what you're thinking about the previous course and see how do you figure out a point is a minimum for the function using its derivative. Okay, first of all, for it to be a minimum, it has to be a critical point. Okay, that's the very important thing. So all the minimums, maximums of this function G will occur at a critical point. Okay, and the definition of a critical point, first of all, is the point where the derivative is 0. Okay, so a critical point of G could be easily figured out by finding the points where the derivative of capital G is 0, which means we're just looking for the points where small g, hence the derivative of capital G, is 0, right? So for the local minimum to exist, we got to find the critical point first. If you look at this graph, there are multiple crossings, okay? It's 0 at this point, it's 0 at this point, and it's 0 at that point. So there are multiple, one point being -1/2, the other one being 3, and the last one being 4. Okay, so we got 3 candidates here. We got 3 such points where it's happening, with x equals to -1/2, x equals to 3, and x equals to 4. Out of which we have to apply the first derivative test to figure out which one is the minimum or which one is the maximum. Okay, so brush up again on the rules that you think about. If you have a critical point and the slope before that was positive, so the graph was increasing, and then after that it's negative, then you have a max, right? That's just the basic intuition. And if you have a critical point, the slope before the point was negative, and after the point it's positive, then you have a minimum. Okay, those are the rules that you want to identify for the critical point here. So let's check. At -1/2, before this point, the slope is negative because the graph is below the axis, right? So if it's negative in this zone, and then after 1/2 it's positive, so you have a negative slope and then a positive slope, you means you have a minimum. So x equals to -1/2 could be a minimum. Okay, let's observe x equals to 3 for a second. When we do observe x equals to 3, what you want to observe here is that the derivative before x equals to 3 was positive because it's above the axis. And then just after x equals to 3, the derivative becomes negative as it's below the axis. So now you have a case where you have a positive derivative, and then a negative derivative. So then that point could only be a max. So in this case, 3 is not a min, it's a max. Okay. So now we're going to look at 4. We're going to look at 4 and see what's happening there. We're trying to see there. Just before 4, the derivative was negative. And just after 4, the derivative is positive. So you have a negative derivative. And then you have a positive derivative at 4. So you know this is going to be a min. So the two candidates that could possibly give you mins are going to be x equals to negative 1/2 and x equals to 4. And this is pretty much the justification they need. Okay, you got to use the first derivative test here to kind of tell them what's happening here. Because we're making our assumptions based off the graph of the derivative. Now is a tough one, where you have to sketch the original function, sketch the capital G of x function on the interval of -2 to 5. Okay, now in this case, we need to extract information from this graph here. We know we can figure out where it's increasing, where it's decreasing, and roughly kind of get an idea of where the max and the mins are. So keeping that in mind, we can actually sketch it. Okay, but there are a few values we got to be very careful of. Okay, those few values are the points where this capital G is 0. Okay, one of the very straight up points that you got to come up with, because this is defined from -2. You know, if you try to find G of -2, what you're going to be integrating is -2 to -2 of small g of t dt. And whenever you see this happening where the bottom bound and the top bound are equal, the definite integral will always spit out a 0. Okay, so you know a point. The point on the curve, by definition, is g of -2 is always going to be 0. In this case, because you're starting at -2. Okay, so we know that point. We know the function's value at -2 is 0. So that's the first piece we got to figure out. Okay, and then we have some critical points we got to make sure we kind of keep in mind. We know the x equals to -1/2 is going to be a minimum. And we also know that x equals to 4 is going to be minimum, x equals 3 is going to be relatively maximum. So we're going to keep that in mind. So try to keep that handy for some time. And then how you draw the graph is depending upon sweeping the information of this graph here, of how this obeys and what kind of is happening there. So what we're trying to see in this case is we're accumulating negative area as we sweep towards the right because we have a negative derivative. A negative derivative between -2 to -1/2 means the function will be decreasing. So if the function started at 0, 0, -2, 0, okay, and it must be decreasing up to x equals to -1/2, then you should have a decreasing curve like this. And then just after -1/2, the function becomes positive, which means the function now must start increasing. So this function will start to increase up, and it'll keep on doing that until you hit 3. Because until 3, the derivative is positive, right? Because it's above the axis. So your function must increase between -1/2 up to 3, because that's the increasing interval, okay? And now we know at 3, it's going to hit its local max value, and then it starts to decrease again. Why? Because in this portion here, the function is decreasing. So you know up to 4, it's going to decrease down to some value, which we don't pretty much know about, but it's going to be a little bit smaller because the function is decreasing, it must decrease. And then just after 4, the derivative becomes positive again. When the derivative becomes positive, the 4 value must start to increase and shut off here, okay, at 5. So this is how you pretty much sketch your graph, where you have to kind of see where you start at first. And then you know when you're starting in this interval from -2 to -1/2, you're going to be decreasing, and there's going to be a minimum of -1/2. So you're going to draw this portion like this. You're going to be decreasing, and there's a minimum and the -1/2. And here, if you draw the tangent, that's going to be horizontal, which means the derivative is 0 too. So that's always matched up. Now, in between -1/2 to 3, your derivative is going to be increasing, okay, and not increasing in a very particularly, manner that I drew up here. It could be a different way. It could be increasing like this, but you gotta watch out that there should not be any critical points. Okay, it could be like a wiggling up like this. It doesn't have to be necessarily like that. So this wiggle can help you like this. So there's going to be a spike. So this is where is the fastest it's happening here. Then it slows down to some small positive number, and then it peaks up fast again at 2, and then it slows down like that. So that's like the rate of change. So you're gonna have some spikes here, some kind of like a non-smooth occurring kind of like thing, but no critical points there. Okay, there could be multiple ways of going like this, there could be multiple ways of going like that, there could be like this or whatever. Okay, there could be multiple ways, but because they're only asking you for the sketch, you can kind of go with whatever you want. That's this. And now after that, we know between 3 to 4 the function must be decreasing, so it's going from its max value to its another local minimum by decreasing, and then from this point onwards on top you're going to get this because it's increasing from 4 to 5. And that's how you pretty much sketch up everything, right? There could be different ways to kind of sketch this. I wanted to give you just a basic idea of what we're trying to achieve here so that you guys can do this yourself. Okay, the reason why I didn't make this very, intense in terms of, talking and discussion, going deep into the arguments, is because I want you guys to scratch the surface yourself. Okay, to kind of try to go dig inside it there, because there's a midterm coming up very soon. I want you guys to be very confident with the topics that you're learning. And if you don't have clarity on anything, I would be more than happy to help you anytime. Okay, so make sure you reach out to me if you have any trouble. And hopefully this tutorial helps you to get started on this. Thanks so much for watching.